Exoplanet science has moved past the era of statistical discovery. Researchers now focus on granular atmospheric characterization, interpreting the environmental dynamics of distant, rocky worlds. But the space-based telescopes we use do not send back pictures of clouds or oceans. They capture photons, and the raw light signals filtered through an alien atmosphere are inherently ambiguous. If a telescope detects an absorption feature indicating oxygen or methane, it is tempting to declare we have found a biosphere. However, an isolated chemical signature remains an incomplete observation. Abiotic planetary processes generate the exact same chemical patterns, effectively mimicking the biogenic signals we are looking for. To translate a raw string of photons into an accurate environmental context, we need a rigorous computational simulation framework. Researchers achieve this by taking three-dimensional general circulation models, the GCMs used to study Earth's climate, and restructuring their underlying code to function as generalized planetary physics engines. By extending these models to handle different gravities, atmospheric pressures, and stellar spectra, we can map universal climate behaviors across a massive cosmic parameter space. ExoEarth simulations provide the necessary context to distinguish a true biosignature from a false positive. They dictate the exact hardware tolerances required for the next generation of space observatories. To build these simulations, scientists start with highly specialized Earth-specific climate models, like the flagship models utilized in the IPCC assessments, and adapt them into a broader cosmic framework. These dynamic solvers retain the core terrestrial physics they were built on, the equations of fluid dynamics, radiative transfer, and cloud physics acting on a rotating sphere. Transforming an Earth-based foundation into an exomodel requires stripping the code of Earth-centric assumptions. The grid's continents are replaced with a global ocean, rotation is locked to the host star, and light shifts to the infrared of an M-dwarf. The model then computes atmospheric behavior, tracing heat transport across the terminator line into the frozen night side. Researchers applied this exact modeling framework to Proxima Centauri Ni, the closest known exoplanet to our solar system. By coupling a fully three-dimensional dynamic ocean to the atmospheric model, the simulation mathematically demonstrated that oceanic heat transport can continuously maintain liquid water on the dark side of a tidally locked world. This continuous oceanic heat transfer provides a liquid lifeline. It expands the habitable surface area of these planets in ways that would be entirely invisible without geodynamic simulations. Because these models inform telescope observations, their internal physics must be rigorously validated against one another to see where their predictions align and where they diverge. The TRAPPIST-1 Habitable Atmosphere Intercomparison Project, or TIE, serves as the critical testing ground for these models. When 4 different GCM teams run identical parameters for the exoplanet TRAPPIST-1e, they largely agree on the planet's average global surface temperature. However, their structural differences cause them to diverge radically when simulating large-scale atmospheric dynamics. TRAPPIST-1e sits precisely at a dynamical tipping point, allowing it to fall into 2 distinct atmospheric circulation states. The first is a fast rotator configuration, characterized by narrow, tightly banded equatorial jets. The contrasting state is a Rhines rotator, where circulation breaks into broad, slower flows reaching higher latitudes. These varying states directly correlate to the simulated transmission spectra displayed below. Furthermore, because the models process upper atmospheric physics differently, they produce vast variations in predicted cloud deck altitudes. Combined, these structural disagreements inject a 50% uncertainty error bar into the expected observations for flagship observatories like the James Webb Space Telescope. This high margin of modeled atmospheric uncertainty directly complicates how we interpret potential biosignatures. It introduces a massive false positive dilemma. For decades, it was assumed that atmospheric oxygen was an automatic indicator of a living biosphere. This flowchart shows the abiotic mechanism occurring on planets orbiting cool M-dwarf stars. It begins when extreme ultraviolet flux from the star triggers the photolysis of water vapor. The intense radiation splits the water molecules. The lighter hydrogen escapes the planet's gravity, leaving behind a massive atmosphere of entirely abiotic oxygen. The models prove mathematically that the detection of oxygen alone is insufficient to verify life. To filter out these dead worlds, Bayesian retrieval systems must rely on secondary spectral discriminators. This overlapping spectral graph targets the 1.27 micrometer band. It shows the specific secondary markers necessary to differentiate an abiotic state from an inhabited one. The presence of O4 dimer features, or unusually high flux levels of carbon monoxide. If we do not simulate these exact secondary markers in advance, we have no way to distinguish a dead world stripped of its water from a thriving biological ecosystem. Resolving those specific secondary spectral branches requires immense optical precision. It shifts the challenge from theoretical physics to structural aerospace engineering. This brings us to the Habitable Worlds Observatory and the exploratory analytic case process currently defining its architecture. Engineers for the observatory are actively using these precise 3D atmospheric simulations to mathematically define the physical hardware tolerances of the telescope. The models demand an extreme engineering requirement. The optics must achieve a planet-to-star contrast ratio of 10 to the negative 10th power at visible wavelengths. That specific ratio is the absolute minimum contrast required to directly image an Earth twin without the optics being entirely blinded by the host star. To maintain that starlight suppression, the physical structure of the telescope requires picometer scale stability across the entire optical array. These simulations provide the mathematical baseline for the structural blueprints of billion-dollar space missions. Classical 3D models are computationally expensive, requiring tens of thousands of CPU hours to reach equilibrium. This limits the number of planetary scenarios we can test. To bypass this bottleneck, researchers integrate artificial intelligence and machine learning to accelerate the modeling pipeline. Deep neural network emulators trained on traditional grids can now predict the complex, three-dimensional temperature fields of tidally locked planets in under 1 second. These AI emulators act as highly efficient, predictive forward models for Bayesian inference engines. This machine learning framework allows researchers to process incoming spectral data and estimate parameters in real time. Ultimately, ExoEarth simulation acts as the mandatory translation layer between theoretical astrophysics and actual telescopic observation. It forces our own terrestrial climate models to mature under extreme stress. It protects the astrobiological community from falling for abiotic false positives. And it physically shapes the lenses and mirrors of our future observatories. By mapping the physics of alien climates, these frameworks represent humanity's first functioning toolset capable of scientifically answering whether we are alone in the universe.